this is kind of where we left off yesterday, and I want to reiterate a couple of important details that, we are defining the velocity as something that we can get from the slope of a position graph. So we would write that the velocity is based on the slope of position and time. The problem with using the delta here is that it chooses 2 points, and we choose the change in x over the change in t for this. The change in the vertical divided by the change in the horizontal, that works great if it's not changing very much. But we know that our graphs can be curved, which means that every single point can be different, which is why we need to write this differently. We don't use the delta, we use the lowercase d to indicate that we're going to do this different. We're going to not actually find a slope, we're going to find all of the slopes. We're going to find an expression that tells us the slope. In fact, I can do this over here too, because we know that the slope of the velocity graph is the acceleration. So I can do the same thing here. I can say that we're going to try and find all of the slopes. Now, there's going to be more to this a little bit. But before we launch into it too much, yesterday I was a little disappointed when I asked you to perform something for me and you were not successful. So today I really need to make sure that I practice on, something we know about. What I mean by that is we have an expression for x. It's 1/2 a t squared plus v naught times t plus x naught. We have an expression for x. If we find the derivative of this function, it should be the velocity. So we should find the derivative of our function with respect to t. This should give us the velocity. Now, don't be alarmed that this is really long. It's a polynomial. So in addition to the power rule, we're going to apply it to a polynomial, which is just 3 terms, in this case, added together. The derivative function is distributed. Just like when you multiply something outside of the front of a parenthesis, you can distribute the derivative. So we're going to take the derivative term by term to get our new function. Let's apply the derivative to the 1/2 at squared first. 1/2, just a number. A is a constant. It's not related to t directly, so A. But now I have my variable, my function variable, t squared. So I'm going to take the derivative of t squared with respect to t. So bring that 2 down, t to the 2 minus 1. There, finished. First term done. Time to go on to the next term. Next term, put the plus sign in there. We're going to take the derivative of this term. The first variable, v naught, is just a variable. It's a number. It's not t, so I just ignore it. Put it down. All right, now t doesn't have an exponent here, but there's an implied exponent, isn't there? Yeah, so what's the implied exponent for t? There it is. So I'm going to bring the 1 down, t to the 1 minus 1. Closing parenthesis. All right, that term's done. Time to move on to the next term. Plus, I don't really think we have to do this one, because I think you can figure out the fact that we're looking at how the function changes with respect to time. And x naught is a constant. Does it change with respect to time? No, its derivative has got to be 0. But let's prove it. Because just because I don't see a t there doesn't mean there isn't a t there. There's a t there. Because I think all of you know that t to the 0 can exist anywhere. Right? So let's follow the rule with t to the 0. Bring down my x naught because x naught is just a constant. Bring down my exponent, 0, times, well, who cares now? Right? Because 0 times anything is going to be 0. So yeah, the derivative of a constant is 0. So I'm going to put the plus 0 there, just so that in your notes you write down the plus 0, so that when you're doing this later on and you go, well, what happened to the 5? I can say it's a constant. We should clean this up. 1/2 times 2 is 1. I'm done. So I'm going to be left with a t to the 2 minus 1 is just 1. Next term. V naught, sure. 1 times t to the 1 minus 1 is 1 times t to the 0. 1 times t to the 0 is just 1 times 1. And 1 times 1 is just 1. So we're done. Now, it shouldn't be a surprise. We expected this. Meaning we expected to turn this into this. This process is here to verify that this is how this works. Questions? Now, I'm glad there's no questions, but that's probably because you don't know what to ask. And I'm okay with that for right now, but consider for just a moment this. Let's get this all out of here for a second.
So the derivative of x equals 1/2 at, that one, is equal to at plus b.
It has to be, though. Because, I mean, when I say has to be, remember, the derivative of this function must be the slope of, must be the velocity. We've said that. So the slopes of the graphs are the velocities, so the derivative must be the velocities. So the derivatives gave us the velocity. More importantly, that continues. The slope of the velocity graph has to be the acceleration. It has to be. So if I want the acceleration, that's got to be d dt of at plus v naught. It has to be. Let's check. First term, take the derivative. Well, that's a times t to the 1. So a times 1 t to the 1 minus 1. Plus, well, the derivative of v naught is just 0. Which, big surprise, the acceleration is the acceleration. Yay. Now, remember, we've been working just with things that are under a uniform accelerated motion. What I need to impress upon you now is that no longer has to be true. Now that we know how acceleration, velocity, and position are related, you don't have to do just these constants. That was a nice entryway into this world, but it doesn't have to stay this way. Moreover, and I want to emphasize this a lot, I am not expecting you just to go this direction. I'm pretty confident that you can probably see your way clear to work this backwards if I ask. That if you could subtract 1 from the exponent, you can add 1 to the exponent. If you can multiply by an exponent, then you could divide by the new exponent. I am thinking that you can work in both directions. Not today, perhaps. Perhaps today we should just kind of focus. And we will. So to focus, let's consider a practice. Now, before I go any further, and I should have said this at the very beginning, this stuff that we're doing here, I want to remind you that the whole goal here is for us to be able to use this to figure out where things move to. That's the goal. It never tells us why things do what they do. It just tells us what they do. What we're going to actually find out is that the things that control motion contribute to acceleration. Forces, energy, they contribute to acceleration. If you can figure out what's accelerating your object, you can figure out the rest. So if you know the influences on an object, you can predict what it's going to do, where it's going to go, how it's going to behave. The other side of that is if you watch something and you see the way it behaves in space, you can predict what must be acting on it. We discover planets by seeing how other planets get moved around. That's how we found invisible things that were in the universe that we couldn't see before. Faith in the idea that if it's moving that way, something caused it. So we're not getting any of the whys right now. We're just getting what's happening. But it's to lead us to understand that when we figure out why things happen in the universe, we can then predict what's going to happen. Also, we stopped at acceleration, but saying that this is the derivative of position and this is the derivative of velocity suggests there might be something out there that is the derivative of the acceleration, the rate at which the acceleration changes. And it is. It's called the jerk. And it's nice to know that there are jerks in physics. I'm one of them. Of course, a couple of years ago, we made our shirt that had this on the front of it, DADT, and it said, Shelty showed me how to jerk. It's probably not an appropriate shirt, but back then it was fun times. Fun times. So we're gonna start with this. And what I would like you to do is figure out the rest. We're not going to calculate the rate of change of the acceleration, so we'll focus. But finish this off. Can you get the velocity function? Can you get the acceleration function? I'll give you a few moments to try it out. Employ the rule, see what happens. Let's see how we're doing. I'm going to find the velocity first, because I have to. I'm going to start by saying bring the 3 down in front. And I have a 2 already there, so 2 times 3 is going to be 6. And now I have to take the 3 and subtract 1 from it, and I get 6t squared. Questions? I'm going to keep going if there are none. All right, go to the next term. Bring the 2 down. 2 times 3 is 6. T to the 2 minus 1 is just t. All right, keep going. Plus, 5 is a constant. So because it's a constant, it's gone, so just 0. Any questions? You sure? Well, we're not done. I suspect you can come up with the next function. So we're going to start over again. This is taking the second derivative of position, the derivative of the velocity. So I'm going to bring the 2 down front. So 2 times 6 is 12. T to the 2 minus 1 is t, and we're done with that term. No exponent on the t means that the exponent is 1. So 1 times 6 is 6. T to the 1 minus 1 is t to the 0. So I'm done. Yes, sir?
With this, would you be able to say that the jerk is 12 meters per second cubed, or is that not a thing?
That's a thing.
Oh,
Now, I want to stop right here for a minute. This process of taking the derivative It takes a little bit of practice, but generally the rule isn't so hard to understand. So you probably need validation. You need to do it a couple times so that you feel like it's, second nature to you. But I want you to know that that is not the end of my expectation. For example, you should be able to tell me when the object is stopped. And that wasn't a suggestion. That's a tell me in 3 or 4 minutes, when is the object stopped? And if you don't know what I'm asking, write the question down, because these are the kinds of questions I'm going to ask, and then you can write in some things that you have to do to figure out the answer to my question. First, I expect you to flesh out all of the 3 functions whenever I give you one function. I am going to expect that I can give you any one of these 3, and you'll be able to fill in the rest. But then I'll ask questions like, when is the object stopped? What I'm asking you to tell me is, what is t when the velocity is 0? So set the velocity equal to 0 and solve for t. There are 2 answers. Yes, ma'am.
When you gave us the top one and we went down, so you gave us a different one, you gave add there.
Yeah, and we'll do that in a bit. We'll focus on just doing the derivative today, but we're not going to stay there. So again, the next thing for you to do is to figure out what the velocity is, what the time is when the velocity is 0. That's this function. Set it equal to 0. Now, I'm using this one purposefully because people get the wrong answer here, even though it's not hard. There are plenty of folks who think the answer is 1, and they're wrong. You can't divide by 0. In this example, you can't divide by t, because you could be dividing by 0. You have to factor out a t. You're not allowed to divide by 0, so you factor a t out, and you set them both equal to 0. And you'll find that there are 2 answers to this question. The velocity is 0 at time 0, and the velocity is also 0 at the 1 second mark. Now, hold on to your boots, because that would never be the question I would ask. I would ask, where is the object when it is stopped? I'll never ask you when it stopped. I'll ask you where it is when it stopped. You will have to know that when I ask that question, you need to figure out when it stopped first, and then use that to figure out where it is when it stopped. That's how I'm going to ask these questions. So I'm going to say, okay, you need to figure out when it stopped, and then put in the times when it stopped to be able to determine where it is. Two minus 3 plus 5 is 4. There are 6 minutes left. I can ask more questions. Like, where is the object when the acceleration is 0? How fast is it going when the acceleration is 0? But what I won't ask you, and this is where all of you kids that are in calculus and stuff should really pay attention, because I should ask the calculus kids to tell me how fast it's going when it's at the origin. And the calculus kids should know why I'm asking that question. If you don't, well, then you didn't have a great experience in pre-calc, because I'm asking you to find the 0 of this function, which is harder to do. That's why you have your graphing calculator, where you were taught extremely well how to figure out the root of a function. Now, I don't care that much about it. I'm saying that if the kids were in calculus now, had pre-calc last year, they learned how to do that. Or they learned how their calculator will show them that. So if I wanted to get some enrichment for those poor kids who are suffering through derivatives and they already know how to do it, well, then you figure out where the object crosses when it's back at the origin, and plug that in to find the velocity because you're so smart. That's why I kind of shut up the smug kids. Want to try again? We got 5 minutes, enough time for another practice, I think. Since this is our last piece before we have our test, I know we're coming in for hopefully a successful conclusion. So here's another function, just practice. It's all this is about, is practice. Yes, Oliver?
Where do we actually get these functions from? Like the 3t squared and all that? Like, where do we find that?
Making them up. I'm going to make this one up too.
Because like in real life, if you gave us an actual like problem, would we actually be able to make those equations, or?
Your question is a little bit premature. So, but you had a course in physics already. So you understand that there might be a group of things that could lead to discovering something's acceleration, a function of the acceleration, of which we could use that then to create the first of these. And then yes, I would expect you to make the others. This has nothing to do with the motion of the object, but can predict the motion of the object. So yes, we could. But that's probably a few months out right now. So, trying to keep you guys inside the realm of possibility, let's go with just want the other functions. How we doing? First one done? Okay, so I think we've got a couple things here. So I'm going to be posting practice. It's going to have this kind of stuff in it. The practice is going to cover going in both directions. So tomorrow we practice a little bit of this maybe, but then we really work on the idea of going backwards if necessary. Because there's something wrong here, and I know you're zipping up because you're just desperate to run in the rain, but you have to notice something. When we did this, we lost information. When I went from here to here, I lost this. Right? It's gone now. Which means that if I gave you just this, and asked you to go back, how would you know to put the 4 here? So this is something we have to talk about tomorrow. The fact that we lose information when we take the derivative. How do you get it back? So Have a good afternoon. You guys are really, really thinking it through. Can you do me a favor here real quick and maybe repeat yesterday's performance, but actually 100% of you get it right the first time without having to be corrected? Which would mean I've presented you with a position graph this time. Can you take what you see in the position graph and create a velocity graph that is of a similar, that tells me the same things? And I'm going to keep talking while you're working because I am really, really hoping that I will not be disappointed this time. But in fourth period, when I started to write out what I had to do here, I saw a lot of erasing. And in third period, I saw less erasing, but that's because I kind of made fun of a couple of kids. And I did that at the very beginning of class, and so everybody was worried that they were next. So, that happens. But did you look at the time equals 0 position? And did you figure out how fast it's going based on the slope of the position graph at time equals 0? And from there, did you choose where on the velocity graph that first dot should go? And then did you pick a place maybe towards the end of the interval and look at the slope of the position graph? And based on how that slope looks, choose an appropriate final velocity for the interval. Because if you're doing that correctly, you should probably note that this has almost a 0 slope, or as close to it. It's very shallow, so that would suggest that that first velocity is close to 0. Now I'm also noticing that every one of the slopes thereafter is negative, suggesting that the rest of my velocity graph will have velocities that are down here. Now, all truth be told, there is no way to know whether the curve for position is changing in a uniform way. But since we've seen nothing else, it seems rather plausible that you might draw something like this to indicate that the velocities are changing and getting steeper all the time, so that your last one is very steep compared to your first one. That would mean that your last velocity is much greater compared to your first one. So I hope this is what you drew, because it's incumbent upon us to recognize that what we're attempting to do is produce a set of velocities that will represent all of the slopes of the position graph. Now, this part is not hard. We know from looking at this velocity graph that there is a relationship that clearly resembles what we see here. We know it because we've seen the equation for a straight line before, and we know that this graph has to have an expression that mimics that of a straight line. V as a function of t is linear, the slope being the acceleration and the y-intercept being the initial velocity. In the same way that the position graph is going to also have threads of things we've seen before. Again, not a surprise. I kind of, I think we know this. We know it because we've done the experiment that shows this too. We've rolled the car, we've taken the data, and we know these things are what are produced by our equipment in order to give us a way of verifying the relationships that are here. Now, of course, we could use algebra, which is what we did, to show that you can start here, and between this and the area, you can produce this. What I want to do today is show you a different way to produce the velocity function from the position function. That's our goal today. And we're going to learn a rule to do this. And it's I call it the polynomial rule, but it's really the power rule. And it works on polynomials. Now, to do this and to be clear about it, I want to divorce ourselves from what we have in front of us and maybe use something that is more fictitious. So I do not want to use x, y, z, or t here, because we already have those assigned someplace else, and there's too much in there, and I want to divorce it. So somebody give me a letter that's not x, y, z, or t, just yell some out. K,
T.
T.
J.
I didn't want to use t, so if we can maybe not use t,
W.
W, and H. Okay. So a number between 1 and 5?
7.
And 7. Okay. All right, so here's our function. And because I want to be more thorough, I'm going to include a number in front of it. And I like the number 2, I guess. So here is a function. Now, I need you to understand that the process we're going to do does require that we pick a particular variable in which to do the derivative with respect to. And what I mean by that is we have a variable that the function is based upon. Looking at this, there's 2 possible derivatives that could be taken here. I could take the derivative of the function k with respect to w. I could also take the derivative of the function k with respect to h. These represent the possible derivatives here. Now, in real calculus, if w and h are related, meaning a change in h causes a change in w, you would have to employ another rule called the chain rule, something that would allow for 2 functions being multiplied together to have their derivative taken. We are going to assume that all of our functions for the time being only have one functional variable, and that the other variables are not related. Okay? Meaning that if our function variable is h, when h changes, w stays the same. That's important for right now. When you're in calculus, we don't have to do that. And later in the year, we're not going to do that. We'll learn the chain rule because we'll have to use it. But for the time being, we're going to say that our functional variables are the only ones that change, and when those are the ones we're working on, the other variables are constant. So, for today, we're going to employ what's called the power rule. And the form of the power rule looks like this. If you're taking the derivative with respect to x of x to the n power, the power rule states this. The derivative will be, you take the exponent and multiply it on the front of the number. And then you subtract 1 from the exponent. So, I take the n, bring it down front, subtract 1 from the exponent, and that's my new expression. So, here's what it looks like in practice. We're going to take the derivative of the function k with respect to w. Okay? Here we go. 2 is a constant. It's just multiplied out front. Just like anything else in algebra, I can just leave it alone and not worry about it. But now we have to focus on the w. The w is the function variable. So we're gonna employ the process. I'm going to take the 2 and put it out front. I'm going to take the w, then I'm going to subtract 1 from the exponent, 2 minus 1. Now I need to keep going because h is still part of this function, but h is a constant. So even though it's there, even though it has an exponent, if it's not related to w, then I just put h to the 7th because it didn't change. It's constant. Now, we're not actually done. We need to clean this up. For example, 2 times 2 is 4. W to the 2 minus 1 is just w to the 1 power times h to the 7th. for WH to the 7th is the derivative of K with respect to W. That's the power rule. Let's try it again. Let's do the derivative again. We have our function now, it's 2w squared h to the 7th, but we're now saying we're taking the derivative with respect to h, so w, that's going to be our constant. So we start the derivative process and we just leave 2 alone. It's a constant. And this time we're going to leave w squared alone. It's a constant. But h isn't. We have to employ our method against h. So open parenthesis, bring down the 7, multiply it out front, and then take my h and subtract 1 from the exponent. H to the 7 minus 1. Now we're going to clean it up. So 7 times 2 is 14, w squared, h to the 6th power. That is the derivative of k with respect to h. So we've taken 2 derivatives. That's the rule. There are lots of these rules. Things that cover all sorts of functions. Sine, cosine, logarithm, exponential. There's lots of them out there. We're going to learn a handful of them, and this is one of them. Now, this is just to get us started. But we already have like